In this video, I want to have a look at solving some probability problems that we can use this binomial theorem for. So this is what we figured out in our last video. So our first example says a certain type of plant has a probability of growing red flowers of 1/3. If 4 of those same plants are grown, calculate the probability that exactly one plant will produce red flowers. So what we're told in the question is the probability of it growing a red flower will be 1/3, which means that the probability of growing anything other than red flowers would be 2/3. And we're also told that we're growing 4 flowers, so that's going to be our n. So then if we want the probability of growing exactly one red, we're going to have 4c1 times 1/3 to the power of 1, or just 1/3, and then times 2/3 to the power of 4 minus 1, which would be 3. And if we pop that in the calculator, you're going to get 32 out of 81 as our probability. In our second example, we've got James tosses a coin 7 times, and we want to find the probability that it lands tails 5 times. So the probability of tails would be 1/2, and the probability of, that should be a P, the probability of not tails would also be 1/2, and we know that our n, our number of trials, is 7. So that means the probability of exactly 5 tails is going to be 7c5 times 1/2 to the power of 5 times 1/2 to the power of 7 minus 5, which would be 2. And if we pop that in our calculator, we're going to get 21 over 128. So this isn't the only way that you can figure out these questions, but it is one of the most simple and straightforward ways that you can do it. Our third example is a little bit more complicated. So we're told that a supermarket sells 5 different brands of tomato paste, including Big Red. Over a 1-week period, 140 people come in and buy tomato paste, and they're just randomly selecting it. What is the greatest number of people that are likely to buy Big Red? And then we're asked to find the probability of this number of people buying Big Red and give our answer correct to 2 significant figures. So first, if we pull the information from the question. So the probability of somebody buying Big Red, well, because there's 5 different brands to choose from and each person that comes in and buys tomato paste is just randomly choosing a brand, that means it's got a 1 in 5 chance of being chosen, which also means the probability of somebody buying something other than Big Red would be 4/5. And of course our n is going to be that 140 because there's 140 people buying it. So what that means is that our expression, if we wanted the probability that our people bought Big Red, we'd write that as 140 CR times 1/5 to the power of R times 4/5 to the power of 140 minus R. Now we want to figure out the highest number, the greatest number of people likely to buy Big Red. Now that word greatest is a little bit of a hint. What we're going to have to do is find the greatest coefficient of this expansion. So when we learn about finding the greatest coefficient, we have this formula that was n minus k plus 2 over k minus 1 times b over a, and we wanted to find when that was greater than or equal to 1. So for ours, our n is 140. So we're going to have 140 minus k plus 2 over k minus 1 times, now in this, when we derived this formula, I actually had these written the other way around. I had my k minus r first as my a term, and then my r term second as my b. So in this, the way I've written it here, my b term is actually my 1/5, and my k term is my 4/5. Sorry, my b term is my 4/5. And we want when this whole thing is greater than or equal to 1. So this section here will just simplify to 1/4. So that means I'm going to have 140 minus k plus 2 over 4k minus 4 is greater than or equal to 1. And working through that, I'd have 140 minus k plus 2 is greater than or equal to 4k minus 4. Bringing the k's all over to the right-hand side and everything else over to the other side, I'm going to have 146 is greater than or equal to 5k. Which will give me k is less than or equal to 29.2. So that means I want the 29th term Now in the 29th term, remember that that r is going to be 1 less than the number of terms it is. So I'm actually going to have 140 C28 1/5 to the power of 28 times 4/5 to the power of 140 minus 28. So what we're actually doing for part A, my answer is that the greatest number of people is 28 people. And to figure out the probability that this number of people buy Big Red, that's where I'm going to evaluate this expression. So if you put all of that in your calculator and round it off to two significant figures, you're going to end up with the probability of 28 people buying Big Red being equal to 0.084 as a probability. One last thing I want to discuss is the idea of replacement and non-replacement. So often when we're calculating probabilities, we need to have a look at how the question's worded as to whether an item is replaced or not in between each trial. And when you've got a small sample set, something like a deck of cards, for example, if you pull one out, then it changes the probability significantly of what's going to happen in the next trial. But if you've got a large enough population, removing one item doesn't affect the probability the next trial round very much. So we can kind of ignore it as long as our population is big enough. So for our last example, we're going to take that into consideration. So we're told that at an election, 30% of voters favoured Party A. If an interviewer selected 5 people at random, what is the probability that exactly 3 of them favour Party A, a majority of them favour Party A, or at most 2 of them favour Party A? Now, because we're talking about an election, that's every single person in the entire country. So pulling one person out isn't really going to change the probability of the next person favouring Party A. It's still going to be about 30%. It's not going to have a very much of an effect at all on that probability. So that means that we can overlook it. All right, so before we start looking at A, we know that the probability of somebody favouring Party A is 30%. So I'm going to write that as 0.3. That means the probability that they don't favour Party A would be 0.7. Alright, so, and we have 5 people. So for A, we want the probability of 3 of them favouring Party A. So we're going to do 5C3, and then we're going to multiply that by 0.3 cubed times 0.7 to the power of 5 minus 3, so 2. And if you pop that in your calculator, you're going to end up with, I've lost my page, 0.1323 or 13.23%. For part B, we want the probability of a majority of them favouring Party A. So that could be 3 of them, it could be 4 of them, or it could be all 5 of them. So 3, 4, or 5, that all counts as a majority. So we're going to have to find all 3 of those things and add them together. So we've already found 3A, so I'm just going to write in my 0.1323. If we hadn't already found that, I'd write out this whole statement. For 4A, I'm going to have 5C4 times 0.3 to the power of 4 times 0.7. And for the 5, I'm going to have 5C5 times 0.3 to the power of 5. Now, I could also times that by 0.7 to the power of 0, but it's irrelevant, so I don't have to write it down. And if I pop all of that in my calculator, I'm going to end up with 0.16308, or we could write that as 16.308%. And for C, we want at most 2 of them. So at most 2 means the probability of none of them, or 1 of them favouring Party A, or 2 of them favouring Party A. Now, if you have a look and compare that to our previous answer, which was 3, 4, or 5, this is all the other possible options. So rather than going through and figuring out 3 calculations altogether, what I can do is I can just do 1 minus the probability of 3A, 4A, or 5A, because those 2 things are complementary events. So that means we're going to have 1 minus 0.16308, which would give me 0.83692, Or I could write it as 83.692%. So that's having a look at a couple of examples of binomial probability.